You are welcome to the continuation of our online tutorial class from your favorite student ScoreBooster, your online tutorial provider on UTME, WAEC, NECO, and NEPTIV exam. For today's class, we shall be considering area expansivity. I am Bangwade. Now, before we proceed, we need to consider the learning outcomes of this particular presentation, which goes thus. At the end of this presentation, listeners should be able to define area expansivity. They should also be able to state the mathematical expression for area expansivity. They must be able to solve relevant UTM questions relating to area expansivity. Now, on to area expansivity. Area expansivity is also known as superficial expansivity. For a solid material in form of a plate, the mean superficial or area expansivity is the fractional increase in area per degree rise in temperature. Now, for a plate of initial area AI, which expands to AF upon the temperature rise theta, then the mean superficial expansivity will be given as beta equals AF, that is final area minus initial, which is AI over AI times delta theta. That since a final area minus initial area is known as delta A, then our beta can also be expressed as delta A, that is change in area over AI times delta T. The units is also per degree Celsius or per Kelvin. Now let's consider the sample questions from the UTME. And the first question we shall be considering comes from 1985, number 18. And the question goes thus. A thin aluminium plate has a surface area of 1.500 meters square at 20 degrees Celsius. What will be its surface area when it is cooled to minus 20 degrees Celsius? Then we are given linear expansivity of aluminium to be equal to 2.5 times 10 raised to power minus 5 per Kelvin. Option A here is 1.503 meters square. Option B is 1.500 meters square. Option C is 1.498 meters square. Option D is 1.497 meters square, while option E is 1.499 meters square. Then on to solution now. The first thing to do as usual is to write out the given parameters, and from the question we are given the initial area A1 to be 1.500 meters square. Then we are given the initial temperature theta 1 to be 20 degrees Celsius. The final area is not given here. Final area is A2, is not given. While the final temperature theta 2 is given to be minus 20 degrees Celsius. Then we are also given linear expansivity to be 2.5 times 10 raised to power minus 5 per Kelvin. Now we have to recall that area expansivity beta is equal to 2 times linear expansivity. And if we apply this, our area expansivity can be calculated from the given linear expansivity. So using beta equals 2 alpha, then our beta will be 2 times linear expansivity, which is 2 into bracket 2.2 times 10⁻⁻5 per Kelvin. Now that we know the value of our area expansivity, then we can proceed to the formula and substitute for the given parameters now. So therefore, using area expansivity beta equals final area, which is AF, minus initial area, which is AI, over initial area, that is AI, times delta theta, that is change in temperature. Then when we substitute for the given parameters, our beta, which is 2 into 2.5 times 10⁻⁻5 per Kelvin, will be equal to final area, which is unknown, that is AF, minus initial area, which is 1.500 meters square, over initial area 1.500 meters square, times change in temperature. Change in temperature, delta theta here will be theta 2 minus theta 1. And since our theta 2 is minus 20, while theta 1 is 20 degrees Celsius, then our change in theta will be theta 2 minus theta 1, which is minus 20 minus 20. So then we can cross multiply. If you cross multiply here, it will give you 2 into 2.5 times 10 is to power minus 5 per Kelvin, then times 1.500 meters square, times minus 20 minus 20 will give us minus 40. Then will be equal to AF minus 1.500 meters square. Then when you evaluate the left hand side, that is 2 into 2.5 times 10 to the power minus 5 times 1.500 meters square times minus 40. Everything will give us minus 300 times 10 to the power minus 5. And that will be equal to the right hand side, which is AF minus 1.500 meters square. Then we can transfer minus 300 times 10 to the power minus 5 to, we can transfer minus 1.5 to the other side to make AF the subject. And if we do that, we get AF equals 1.5. The minus will now become plus. When it goes to the other side, will be 1.500 meters square plus 300 times 10 to the power minus 5. So minus 300 times 10 to the power minus 5. When we make AF the subject of formula here, so it will make us transfer 1.500 to the other side, and that will give us minus 300 times 10 to the power minus 5 plus 1.500. So if we rearrange it, we have AF, which is final area, equals 1.500 meters square minus 300 times 10 to the power minus 3. 300 times 10 to the power minus 3 is 0.003. So making our answer to be AF equals 1.5 minus 0.003, and that will give us 1.497 meters square, making option D the correct answer for this particular question. The next question we shall be considering comes from the year is not specifically quoted here. We have the question goes thus: we have a square plate of size 10 centimeter is made of a metal of linear expansivity of 2 times 10 raised to the power minus 5 per Kelvin. As the plate is heated from 30 degrees Celsius to 100 degrees Celsius, the area of one face of the plate will increase to dash. So we have option A here to be 100.1 centimeters square, option B to be 100.3 centimeters square, Option C is 101.4 centimeters square. Option D is 102.8 centimeters square. Now on to solution. The first step is to write out the given parameter as usual, and we are given the initial length Li or L1 to be 10. From there we can calculate the area. Since they say it's a square, an area of a square is L square. So if L is 10, then its area will be 10 square, which is 100 centimeters square, making our initial area to be 100 centimeters square. From the question, we are also given the theta 1 initial temperature to be 30 degrees Celsius, and we are given the linear expansivity to be 2.0 times 10 raised to the power minus 5, and also we are given the final temperature to be 100 degrees Celsius. Why the final area is not given? Of course, that is what they want us to find. As the question says, the area of one face of the plate will increase to, that means they want us to find the final area. Now, as usual, we can calculate our area expansivity from linear expansivity given by multiplying it by 2. We have to recall that we said area of superficial expansivity equals 2 times linear expansivity. Therefore, beta equals 2 times alpha. So our linear expansivity in this case also will be 2 into 2.0 times 10 raised to the power minus 5 per Kelvin. Now the next thing is to proceed to substitute for the given parameters in the area of in the formula of area expansivity, and we have to recall that the area expansivity beta equals final area, that is AF, minus initial area AI over initial area AI times change in temperature, which is delta T. So if we substitute for that, our beta, which is our area, will be 2 into 2.2 times 10 raised to the power minus 5 per Kelvin, equals final area, which is not given, minus 100 centimeters square, that is our initial area, over initial area, which is 100 centimeters square, then into change in temperature. Our change in temperature as usual will be theta 2 minus theta 1, final temperature minus initial, and that is equivalent to 100 minus 30 degrees Celsius. Similarly, we can cross multiply. So if you cross multiply, you get 2 into 2.0 times 10 raised to the power minus 5 per Kelvin, then times 100 centimeters square into 100 minus 30 will be equal to AF minus 100 centimeters square. Then when we evaluate the left hand side, that is 2 into 2.0 times 10 raised to the power minus 5 times 100 times 100 minus 30. Everything will give us 4 times 70 times 10 raised to the power minus 5. 2 times 2.0 will give us 4. Then times 10 raised to the power minus 5 we have at the back, that is for our area expansivity. Then times 100 centimeters square into 100 minus 30 will give us 70. So when you evaluate this, the left hand side at the end of the day with calculator we get 0.28, which is equal to right hand side, that is our AF minus 100 centimeters square. So we can make AF the subject by transferring 100 to the other side to get AF equals 0.28 plus 100. So making our AF to be 100.28 centimeters square, which can be approximated to 100.3 centimeters square, making option B the correct answer for this question. Now our next video will be on volume expansivity with sample questions and solution from UTME. I urge you to please subscribe to our YouTube channel, like and share our videos, as we promise to be providing you with more interesting lectures on subjects relating to UTME, especially physics. Thank you.